12.4 is on statistical measures. So the first definition we have is a random sample. So if I'm trying to figure out, I don't know, how many people are going to vote for the next mayor of Indianapolis, and how many people are going to vote for a particular candidate. If I'm going to go out, do you think I'm going to interview or talk to every single person in Indianapolis? No, right? So a random sample is basically a smaller size sample. So it's a sample in which all members of the population have an equal chance of being in the sample, and it's a smaller sample than the total population, okay? So data can be divided into two types. So we can have quantitative data and qualitative data. So these are our next definitions. So quantitative involves the word quantity. Think about what the word quantity means. It's usually some type of number, right? So this is numerical data. And then qualitative data uses the word quality. This is something that's categorical in nature. So you could say something like, oh, that person, they're in the blue eye group, they're in the brown eye group, they're in liberal, moderate, conservative, right? They're in the, what was the cool chicken group? Oh. Poultry pals. They're in poultry pals. They're in theater. They're in soccer, right? These are qualitative in nature. All right, so quantitative data can then be further divided into two classifications. So we have discrete data and continuous data. So this is something that's a little bit tricky for people to understand, okay? Continuous data is things like the weight of water. So if I have a cup and it has water in it, I could say that it's, you know, I don't know how many pounds, 0.5 pounds, but it could also be 0.523 pounds, right? So there's no like minimum difference. It's not like saying, for instance, like a shoe size. When you guys all say your shoe sizes, what do you all say? Like 8, 8.5, 9, 9.5. Do you guys get that? Does anybody in here say that their shoe size is 9.136? No. That's really weird, right? So discrete data is the ones where there's those set numbers, like 9, 9.5, 10, right? And continuous data is one that can kind of move up and down like a scale. Imagine like a thermometer, it can go up and down between different temperatures, right? And there's no minimum difference between the two values. So can you guys think of some different examples of discrete and continuous data? I don't know. Think about things that...
Shoe size.
You already said shoe size, Jacob. What else? Yeah.
Like, you don't say, oh, there's 2.3 people.
Yeah, you don't say there's 2.3 people in this
Like
room. That's weird. Right? So like population, definitely. Christine.
I would say I'm 14.3 years old.
Yeah, you don't really say, I'm 14.37 years old. You might say like 14 and a half, 15, but I've never heard someone say like, I'm 14 years, 2 months, 3 days, 22 seconds, and 32 milliseconds. That's very strange, right? So like your age would definitely be like a discrete data. Anything else? I don't know. There's lots of examples out there. Okay, so let's try some of these. So number one, so it says identify data as either qualitative or quantitative. If it's quantitative, we're going to break it into the discrete and continuous. So the number of answers that you, or the number of questions that you answer correctly on a true-false test. What do we think? Do we think it's qualitative or quantitative? It's a quantitative data, right? And do you think that's discrete or continuous?
Discrete.
Yeah. So the weight of each animal in the zoo? Quantitative. And this one's kind of tricky. It could kind of be discrete or continuous, right? I would think it's continuous. Because really, if you're measuring the weight of an elephant, I'd be like, oh, it's this many tons. But what's the smallest animal in a zoo? Like one of the little fish, like one of the Nemo fish, the clownfish. Maybe I don't use tons. Can you imagine if I used tons to weigh that little Nemo fish? 0.00000. Then now you're definitely seeing why it would be continuous, right? So this is going to be continuous. All right, so a person's blood type. Qualitative, exactly. All right, so the frequency of an element is the number of times a particular value occurs. So I could go out and talk to my friends and be like, yeah, my Algebra 2 students, 10 of them got A's. And my friends would be like, I don't know what that means. Like 10 people got A's. How many Algebra 2 students do you have? Do you understand? If I had 11 Algebra 2 students and 10 of them got A's, that would be really good. But if I teach 100 Algebra 2 students and only 10 of them got A's, that's not very good, right? So frequency is the number of times something happens, and relative frequency is relating it to the whole, like how many it's out of. So the frequency, if it says 4 earned A's, 11 earned B's, 7 earned C's, and 3 earned F's, and it says there's a total of 25 students, the relative frequency would be 4 out of 25, 11 out of 25, 7 out of 25, and 3 out of 25. Yes?
And then we'll grade things in A, B, C, D, and then
Oh, we don't have D's, do we? We do F's.
Is that a bonus point?
I don't know. Is that a bonus point?
No.
All right.
First bonus?
So make a bar graph of the data from example number 1. So
Thanks, guys.
I know he's mad. So let's say we go at 2s. 2, 4, 6, 8, 10. I should really go to 12. Okay, so for the A's, we had 4 that got A's, right? We had 11 that got B's. Oops, make that kind of between those two. 11? I tried. It's hard. Let's see. C, we have 7. And then we have F is 3. All right, so that's our bar graph. It might be a histogram. I think histograms are the ones where there's spaces in between them, and bar graphs are the ones where they're smushed up next to each other. I don't know. Are these weird like definitions? Bar graph or histogram, whatever it is. All right, so common distribution shapes. So if we drew things as bar graphs, let's say, something that would be uniform would be where all of the data values have approximately the same frequency. Okay, so that would be going straight across. So all of these are kind of the same height. Symmetric is where the left and right sides would be like mirror images of each other. So maybe something like that. Or, I mean, you could have really anything, like just as long as they're mirror images of each other. So you could have something like that for data. All right, so, and if it was a bar graph, maybe like some like this, that would work. Lots of things can be symmetric. Okay, skewed right is the opposite of what you probably think it is. So skewed right, I would think that all of your data is on the right. It's actually on the left. So it's where the tail is on the right. So something that would be skewed right would be something like this. So the tail is on right. Oh, dang it, I just did it the wrong way. Dang it. Now I've like confused myself because I'm telling myself it's the opposite of what I think it is, but I now know. So the tail is on the right. And then skewed left is the other way, so it's like this. All right. So number 1, it says, from the 4 common distribution shapes, choose the best distribution for the data. So A, the ages of people in an elementary school during a typical school day. So we're going to include all the little kids, but we're also going to talk about all the faculty and staff. So do we think that most of the ages are big ages, old ages, or younger ages? Yeah, so what do you think it is? Yes, exactly. It's going to be like this. The bulk of the data is over there on the left, so we call this skewed right. Basically means things are more spread out on the right-hand side. All right, the age at death for all people in the United States. Yeah, that's going to be the other way, right? Skewed left. So this isn't saying that there are no old people in an elementary school and that people do not die young. It's just saying the bulk of people do die when they are older.
So, like,
Why is it opposite?
well, I mean, so let's, in the death example, like, what would be the thing rising?
Like the mean. So the average age would be here. And we'll talk about that little M thing in a second. That's called the mean. So like if I talked about, I don't know, I found all of your relatives and we talked about how old they were when they passed away, I would say the average for this class would probably be like 80 years old, right? Does that make sense? Like much older. All right. So C, the day of the week of all students' birthdays in a school where Sunday is 1, Monday is 2, etc. Do you guys know what day you were born? Yeah, Christian?
Actually, Monday, but I do know that it is skewed right.
Uh-huh.
Watching the
from watching the video. Actually, I don't know. Yeah, it's kind of weird. I would say uniform mostly. It's mostly uniform. Like there's probably about a seventh of you that were born on Sunday, a seventh of you that were born on Monday. But the thing I do mention in the video, I think, is that it's actually not uniform. You would think that it's uniform. But sometimes doctors make you wait until Monday to come in. So labor is very long, and sometimes you just kind of have to wait it out. Or they'll schedule C-sections and things. Not on the weekend. So that happens. All right, so the IQ scores of all the men living in the United States. What do we think?
Symmetric.
Yeah, it's symmetric. So that's going to be something that we call the bell curve. So it's going to look like this, with kind of an equal amount that's super bright, like savant level, an equal amount that has a very low IQ, and then the bulk of the people are in the middle, with the mean being in the middle. So the average is in the middle. All right, and an outlier is a data value that is so far removed from the rest of the data. Sometimes these are removed from the data so they don't mess up your results. So I had a friend who was finishing her thesis in optometry, and she was researching like 2- and 3-year-old kids. And she had something that she thought was true, but when she did the research, there were enough people that were outliers that she had to stop her thesis and not do it on that because it clearly wasn't able to be proven. So if you have a lot of outliers, it messes up your data. And then someone in the first class Kyle brought up the fact that when you talk about millennials and their average income, there's one millennial who messes that up.
Mark Zuckerberg.
Yes, Mark Zuckerberg. So because he makes so much money, you can't include him in the average because he's going to make it look like millennials make an average that's much higher than what they actually make. So there are outliers that sometimes you have to remove because they're messing up the data. All right, so a supermarket manager wants to know how long customers are waiting in the express lane. So a random sample of 15 customers is taken, recording wait time in minutes. Create a stem plot of the data below and discuss its shape. So stem plots a lot of times are used for 2-digit numbers. So if I wanted to do it 75, I write it like that. 81, I write it like that. But if I have 83 as well, I put it in the same line here. So it's like 81 and 83 are listed. Okay, so it's kind of weird. Have you guys seen these before? Stem and leaf plots. All right, so our stems, our first digit, so the number before the decimal place in this case, is 0, 1, we have some 2s, and we have some 3s. We don't have any 4s, right? Okay, so we're going to go through here. So we have 3.1, 1.1, 3.1, 3.2, 0.5, 3.2. Do you guys see what I'm doing? So each time I'm reading a number, I'm putting the second number in the stem and leaf plot. 3.4, 2.8, 3.2, 3.4, 3.1, 2.3, 1.7, 2.1, 1.5. And then we put them in order. So we have 0, 5, we have 1, and then we have 1, 7, 5. 2 had 8, 3. Oh, what am I doing? I'm just rewriting it. 1, 5, 7, 2, 1, 3, 8, and then 3, 1, 1, 1, 2, 2, 2, 4, 4. Yeah, okay. I don't know if that was Greta or Jacob, so do both. All right, I'll think about Caleb. All right, so discussing its shape. What shape do you think this is? Skewed left, right? Because most of the data is over here on the longer side. Do you think that's what the supermarket would want? No, it probably wants the data to be skewed right, so it's waiting less time. So they would probably investigate that and find ways to make the lines shorter. All right, next up, so the mean. We all know how to find the mean, right? The mean is the average value, right? So we say that it's a measure of central tendency. So mean, median, mode are all measures of central tendencies. Okay, they're denoted by a mu or an x with a bar on top of it. X bar. That's how we read that. A mu is a Greek letter. It looks like an M and it looks like a U. I don't know if that's why they call it mu. I like to think it is. It's not. But so it's an M and it's a U. So do you like my cheesy joke? Mu. All right. So if we're finding the mean, we just add up every single number and we divide by the number of numbers, right? So the way we write this out is we say x1 plus x2 plus x3, and then we do dot 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 plus x sub n, and we divide by how many? N. We had n data sets, right? N points. All right, so the median. The median is also a measure of central tendency, and it's just the number that's in the middle. But if you find the number in the middle, and let's say there's two numbers, like 8 and 10, what do? Yeah, you take the average of those two numbers. Do you guys remember that from your I-step days? Did you guys take the I-step? And then the mode is the number that's there the most. Okay, so basic example, I hope that you all know and have seen this before. So find the mean, median, and mode of these numbers. So I typically put them in order. So I have 2, 2. I have 3, 3, 3. I did this on purpose. 3 3s. I have 4, 4, 4, and 4. 2 5s and a 6. So if we're finding the mean, we add all those numbers up and we divide by the number of numbers that we have. So we have 12 numbers. I think the sum is 45. Is that right? Did you guys find 45? So what do we get when we do 45 divided by 12?
3.75.
Now our mode is the number that was the most. What's the number that's the most? 4. And then our median is the number that's in the middle. So did you guys always do this when you're in school? Cancel, 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 cancel. And then you can also do like 2 at a time, 2 at a time. So we have these 2 4s in the middle. Well, what's the average of the 2 4s?
4.
It's 4, right? So our median is 4 as well. And in most good data sets, the mean, median, and mode are kind of close to each other. Sometimes the mode's not, but. All right. So there can be several distributions that have these same central tendencies. So all 3 of these in the main plots have the same central tendencies. My 159 will move it up there. So for instance, all 3 of these stem plots have the same center, which is 105, and the same, so that's the same median and mode in this case. So the data does have a different spread though. So the one that's probably the most accurate data, I would say, is the one on the far right. Do you guys see the one on the far right? They're all really close together. Okay, this one is not super accurate. Like if I was trying to predict something on this, I don't know. Maybe a person would be like 91. I have no idea. Does this make sense? So it's important to not only consider like these central tendencies, but also to consider how spread out it is. Okay, so this is where we talk about variability. So the second plot has the largest variability because it's really spread out, and the third has the smallest. And there are 3 ways to measure variability. So we can use standard deviation, range, and interquartile range. So range is the easiest. All we do for range is we find the difference between the largest value and the smallest value. So Maya, what's the biggest value in this table? What's the smallest value in this table? This time. 125. And the smallest? 85. So what's the difference between 125 and 85? 40. So then what about this one? 145 and 65? 80. Yeah, so this range was, the first range was 125 minus 85, and we got 40, and this range was 80. What about the last range? 119 minus 95? 24, is it 24? Yep.
No, it's 91.
Is it 91? Oh, it is 91. Man, I was going with it. All right. I don't know. If someone tells me the wrong thing, I just go with it. I don't count that as my mistake. I was just going with it. All right, so here we go. So the range is the difference between the largest value and the smallest value. And then the deviation. Dang it, 28. Okay, you will get that one. All right. All right, so I think he was telling me it, right? Were you saying that? Okay, whatever. So the difference of a data value xi and the mean is going to be like the mean, which is x bar, minus x sub I. You could also write it as mu. I usually write the mean as mu. I don't know, I'm just used to writing mu a million times, so if you don't like writing mu, that's fine. All right, so this is a little confusing. So let's say I was doing, do you guys remember a long time ago when we did scatter plots? So maybe the scatter plot in our line of best fit was there. If we talk about how far each of these points is from the line, this one's super close to the line. Do we agree? This one's pretty close. This one's super far. But maybe this one and, I don't know, this one, maybe they cancel each other out because one's above and one's below, so they kind of even each other out, right? So we want to find a way to get rid of the fact that points that are really far away might cancel each other out, because we don't want that to happen, because that's messing up the variability thing. We want them to be really, really close to the line. Okay, so what we do is we take each distance from the line, and then we square it. Okay, so tell me, if I have 1/2 and I square that number, what does it become?
1/4.
It's 1/4, right? So it gets smaller. So if something's really close to the line, so if it was 1/2 away, it's now even smaller when we square it. But if something was 9 units away, that becomes 81. That like accentuates the fact that it was far away, right? So in order to find the standard deviation, which I will have you find one by hand, you follow these steps. I will always give you these steps. So we're going to try one. So it says find the population standard deviation of this data in the stem plot below using the steps above. Then use a calculator to find the same results. Okay, so what we're going to do is first is we're going to find the average, the mean. Okay, so remember these are the numbers 81, 87, 92, 94. So we're going to add these together. So I think I had 752, and when I divide by the number of numbers, 1, 2, 3, 4, 5, 6, 7, 8. Do you guys see where I get that? Counting these, 1, 2, 3, 4, 5, 6, 7, 8. You should get 94. Yep. So now we're going to go through a process. So we're going to take each number minus the mean, and then we're going to square it. Okay, so I don't care how you represent this data, how you put this all together, whatever you want to do. So we're going to do 81 minus 94, and we're going to square it. Then we're going to do 87 minus 94, and we're going to square it. Then we're going to do 92 minus 94, and we're going to square it. So I just usually write all of the subtraction steps first, and then I go back through and I square them. You could do all of this without a calculator, I promise. Oops, minus 94. Okay, so when I subtract 81 minus 94, so 94 minus 81, what is that? Negative, or 13, so negative 13. How about this next one? Negative 7, yep. Negative 2, 0, 2. All right, we can all do that, right? Now we square them. Really, you should put parentheses around those negatives, right? So when we square them, we get 169, 149. Oh, not 49, thank you. 4, 0, 4, 9, 49, and 100. Okay, so right now we're through this step. So we found the mean, we found the deviation for each data point, we squared each of them. Now we take the average of these numbers. So for these blue numbers that I have, I find their sum. So I add them together. So I got 384. And then I divide by the number of numbers I have. So divide by 8. I got 48. Last step, you take the square root of that number. So we get 6.928. This is what I call the standard deviation. So the standard deviation, in order to notate that, I think I left off a blank. We use the Greek symbol sigma. Now you guys know what sigma looks like from the last chapter. It looks like this, doesn't it? Doesn't it look like sigma? But that's not what we use. We use the lowercase one. So there's uppercase and lowercase in Greek letters. So confusing. And it looks like an O with a little line on top of it. So it's like this. That's sigma. All right, so this is all equal to sigma. Okay, so this is what we call the population standard deviation. So when you take AP Stats, which hopefully you guys all do, Don't tell Maury I said that. All of you take AP Calc, right? Yes. We fight about which class is better all the time. I believe AP Calc is, he believes AP Stats is. But there's two types of standard deviation. So Maury got really mad one time because he was like, why are you teaching them this way when it's just this standard deviation? I'm like, well, what if it's like the actual population? So if you're going out and you're surveying a certain population, you use the standard deviation I just did. But for some reason, if you're doing a random sample, like if you're just randomly talking to a certain people to represent the whole thing, we use a different standard deviation. And I'm sure he'll explain that to you in AP Stats. So instead of dividing by 8, which we divided here, we do one less than it. I like to think of it as the Mark Zuckerberg, like taking him out of the equation, getting rid of those outliers. So we would take that 384 that we found and we divide by 7 instead. So if we did 384 divided by 7, and then we take the square root, we get 7.407. Did you guys get that? Yeah, so that would be the standard deviation. Okay, so they're a little bit different. All right, last concept. This is an easy one. Quartiles. Any idea what quartile would mean? A quarter, right? So we're thinking about four regions. And it's basically like the median. We just do it several times. So we find the first median, and then for each side we find the other two medians. Okay, so the first thing we're going to do is we're going to write these numbers in order, which sometimes that's the hardest part, the most annoying part. So we have 2 and 2. And then we have 3 and 3. How many 4s? 1, 1 4, 2 5s, a 6, a 7, an 8, oh, 2 8s, 3 8s, and then we have 9 and 9, then we have 12, 13, 14, and 15. All right, good. Thanks for your help on that. They're totally tiny. I have a hard time with those. All right, so first we need to find the first median. So we're going through, and you can do this with just your fingers, but you're crossing these out, right? So go work your way in. So cross out, cross out. Are you getting there? So what are we between? Yeah, we're between the 7 and 8. So what's our median? We call this Q2. Okay, now we find the medians of both of those halves. So on this left side, we're going to go 7 and 2 go away, 6 and 2 go away, 5 and 3 go away, 5 and 3 go away. We're left with 4. That number's in the middle. That is called our Q1 because it's finding the separation for that first quartile. And do the same thing for the next one. Where are we at for that? 9. That's our Q3. So our inner quartile range is Q3 minus Q2. Or Q3 minus Q1, I mean. So 9 minus 4, which is 5. It's the third way to measure spread. That's the easiest way, isn't it? Isn't that easy? Much easier than standard deviation. All right, and then there is a way to do this on your calculator. I'll teach you guys that another day, though. So the one you do on your homework doesn't involve the calculator.